Hey, guess what time it is, class? It's science time. Now, take out your notes and let's get learning. Hey, class. Welcome back. Today we're going to be starting a new section of reaction rates and rate laws. And the other day you should have watched the video talking about what factors would influence the rates of a chemical reaction. So now we're going to be getting into a little bit more of the specifics of it. Now this can be a rather in-depth type of subject, and we're going to go a little bit in depth, but not as far as this could possibly go. So this is something that if you're planning going into taking any type of college chemistry, this is a good thing to know. And there's also a lot of applications not only in chemistry but also in biology and also in physics here too. So this is something that is studied in many different subject fields. So let's go ahead and get started. So the one thing I also want to draw your attention to is if you look at the very first page, we're starting with a compound that is purple, symbolized as being purple here. And as we see it begin to progress on, it is beginning to flip over to more of a green compound. And if you graph it out, you end up having a high concentration of this purple compound, then also drops off rather significantly, which you can see over here. And then as time goes on, there's less and less of the purple. But in the meantime, you start off with no green at the very beginning, and then as time goes on, the green product is beginning to increase until finally it maximizes and there is no more of the purple compound here. So now there is a way to go about and measure those rates of change. So this should be a little bit of review. As a matter of fact, you encountered some of this during Chemistry 1. If you remember the iodine clock reaction, that's the one where you mix the three solutions together and you timed it, and all of a sudden, at a set period of time, the solution would change from colorless clear to a dark purple black color almost. So and then you were trying to manipulate different types of factors here that would affect the rate of change. So in chemical kinetics, the speed of a chemical reaction is called its reaction rate. In other words, how quickly does that happen here? So the rate of reaction is a measure of how fast a reaction makes products or uses reactants. So you could either be looking at the product side or you could be looking at the reactant side. So the ability to control the speed of a chemical reaction is important. And especially in different types of industry, sometimes they want the reaction to occur quickly, and sometimes you don't want to go too fast. For example, like the production of ammonia. If you make ammonia too fast, it can become explosive. But yet, the production of ammonia is very important from anything from explosives to fertilizer. And so, but the process of manufacturing ammonia, they want to control that speed very carefully. There's a lot of different types of industry here where they want to control a reaction fast enough where they're able to get a good product, but not too fast where it becomes dangerous. So there is a lot of manipulating that has to go on. So some of the factors that would influence how quickly a reaction takes place. First of all, the physical state of the reactants. In order to react, molecules must come in contact with each other. So the more homogeneous, in other words, the more evenly mixed the mixture of reactants, the faster the molecules can react. And so, for example, if you look at a Bunsen burner, and if you remember when you first light the Bunsen burner, you have an orange flame, and as you begin to introduce oxygen, it goes from an orange flame eventually to a blue flame. So initially, when you light the burner here, it's a rather heterogeneous mixture, which means you're going to have a large amount of fuel here, and the oxygen is on the outside. But when you begin to open up the oxygen, the air intake at the bottom, the fuel and the oxygen become more evenly distributed, and you get a much hotter flame, which is taking place here. So the more evenly mixed the material, or the more homogeneous, the better the reaction. The more heterogeneous, typically the reaction is less efficient. So some other factors that affect the rate of reaction is how concentrated the concentration of your reactants. So as the concentration of reactants increases, so does the likelihood that the reactant molecules will collide. So for example, if you burn steel wool, typically if you burn it on the outside, you don't blow on it, you don't fan it, these things will go at a decent rate. But if you take the same thing and you put it into a container of pure oxygen, this thing will burn very brightly, almost blindingly, and it will produce so much heat. Sometimes it will crack the glassware. You would have molten metal dripping on the bottom of it. So, how concentrated are your reactants will determine the rate of reaction as well. Temperature is perhaps one of the biggest factors that will affect the rate of reaction. So typically, the warmer it is, the more collisions, the more energetic they are, you're going to have a faster reaction. The colder it is, there's a lot less energy, and the reaction tends to take place a lot slower. So as you can see with a glow stick, that if you put this into cold water or into ice water, it will begin to dim. Or if you take a glow stick and if you're stuck it in a freezer, um, it'll glow, but it's very, very dim. But if you take the same glow stick and you put it into very hot water, then the glow stick will get very bright. Then normal air temperature, it'll be bright, but not nearly as bright as when you put it into hot water. If you ever do this, just make sure that you don't put it into boiling water. You don't want to leave it unsupervised in a pot of boiling water here. And whatever you do not microwave it. But it's kind of a neat thing here. But one thing you will notice here too is that if you put it into hot water, it not only will glow very brightly, but it doesn't last nearly as long. You put it into cold water, it will be very dim, but you can make it last for hours longer. Also, the presence of a catalyst, and what a catalyst does is most often it will help speed up a reaction. It makes the reaction become more efficient. So by changing the mechanism of the reaction here, so catalysts themselves are not consumed in the reaction. They're basically a surface that allows the atoms or molecules to come in contact with the surface, and the catalyst will help arrange the atoms and molecules in just the right position so they are able to more effectively combine together. Because if you remember um, with the collision theory, is that they have to be oriented in the right direction and impact at the right have the right energy level, or have to hit impact at the right speed. What a catalyst does is that it gives a surface where these atoms and molecules can attach onto. They're going to be oriented in the correct direction, and in doing so, they're more likely to combine. Now, what most people don't realize is that there's also anti-catalysts as well, which actually will do the opposite, um, where they make it more difficult for the atoms and molecules to combine here. And so, typically for chemists, you know, sometimes they're looking for catalysts to help speed up a reaction, and sometimes you're even looking for anti-catalysts to slow down a reaction. So it depends upon what you're trying to do. Now, what we have here is a catalytic converter, and this is on the underside of a car. It takes the gases coming off of the engine, which has a large amount of very toxic type of gases. It passes through this almost like a honeycomb wafers or like a grid here. And as the gases pass through here, this honeycomb wafer is lined with platinum, a very precious metal. And it takes those noxious gases and breaks them down into something that is less dangerous. Um, Now, you could get rid of this, and the gases from the engine will go off into the atmosphere, which would be very dangerous, especially in the more populated areas. And the chemicals will, some of them will break down over a period of time, but sometimes it'll take them days, weeks, or maybe even years. This does it in a fraction of a second. So, what normally happens naturally over very long periods of time, this can do it in just less than a second. So the rates of reaction can be determined by monitoring the change in the concentration of either reactants or products as a function of time. So, if you're looking at a chemical here, so a red chemical converting into a blue chemical, and if you take a measurement at regular intervals of time, you can find out what is the concentration of each one of those. So the reaction rate here is you're looking at how much of a change is taking place within a period of time. So in this reaction, the concentration of butyl chloride, which is CH4Cl, was measured at various times. So every 50 seconds, this butyl chloride, the concentration, if you remember here, the square brackets means concentration of. The unit here is most often going to be in the unit of molarity, which is a mole per liter. And so what they end up doing here is that between these two increments of time, the rate of change was 1.9 times 10 to the negative fourth molar per second, or molarity per second. So that is every 1 second, the concentration was changing by 1.9 times 10 to the negative fourth molarity. So now one thing to notice here too is look at how these values are changing here. So when we're looking at the concentration of this, what we're looking at is how much is the concentration changing within a period of time. Now, if you've taken physics, you should be familiar with this. If you have not taken physics, I would highly recommend that you do so. But so when you're defining a rate is how much a quantity changes in a given period of time. So the one that a lot of people are aware of is with driving. So the speed that you drive your car is a rate. So you're looking at the rate. So you're looking at the distance your car travels, which is a lot of times around here we measure in miles, other places kilometers, in a given period of time, which is a lot of time in an hour. So the rate your car travels is the unit of miles per hour. And the way that we go about measuring speed is change in distance over the change in time. And again, if you remember the triangle here, the triangle is a capital delta, which means the change. So you're looking at how much is the distance changing versus how much is the time changing. So if you traveled 50 miles in 1 hour, you traveled 50 miles per hour. If you traveled 100 miles in 2 hours, so 100 miles divided by 2 hours, it'll still be 50 miles per hour. So you're looking at how much distance you should travel given a specific period of time. Now, you're also going to be encountering average versus instantaneous. So whether you're talking about average versus instantaneous velocity, in physics, we also have the same thing with acceleration. But here we're going to be looking at the rate of chemical reactions here. So we're looking at the molarity per second. Now, a couple things to keep in mind. Instantaneous is basically, using the analogy of a car, is whatever you see whenever you look down at your speedometer. So you look down, and however fast you're going, that's your instantaneous speed. The average is kind of like saying, okay, I live so many miles away. It takes a certain period of time to get there. And so if you take that distance divided by the time, that is your average. That does not take into account all the stop and go that you're doing. Because sometimes you may have gone up to 60 miles per hour, and other times you were at a stop. And then other places you're going 25 miles per hour, and then all of a sudden you're slowing down, you're speeding up, you're slowing down. So the average does not take into account all of those things here. All the fluctuations, if you look at every moment in time, you're looking at your instantaneous. So whenever you're looking at your speedometer, you're looking at this. How long does it take to get there? And ignoring all the fluctuations, you're looking at your average. So with the instantaneous, the measurements are taken at only 1 point in time. And the key thing is only taken at a 1 point in time here. Emphasize this. So this is taken at only at 1 point. So on a graph, you'll have a single point, and you have to find the slope. So hopefully, a little bit of your math here, you're going to be finding the slope of that line. that is drawn tangent, and again, tangent is kind of the key thing here, to the point on the graph. So if you have something where you're going at a certain distance and you're arriving at a certain location here, you have this downwards straight linear line. So if I want to find out how fast I'm going right here, I draw a line that runs tangent to that line. Well, in this case, the tangent is basically a straight line applied onto a graph. So that touches the point that you are going to be measuring. So in this case, I want to know at this point in time right here, how fast am I going? I just draw a line that runs tangent to that line, and then I measure the rise versus the run. And so that rise versus run gives me my slope, which is what we define as being the rate of. Now, if you have something which is a curved line, for example, let's say you're traveling along, you're slowing down, you're slowing down, you're slowing down, your distance is dropping, and eventually come to a stop. And at this point in time, I want to find out how fast am I going. Again, you draw a line that runs tangent to that arc here. So that's this line right here. So from here, let me see if I can draw a straight line here, to roughly there. Now that should be only touching that point. That line should only be touching the point right here. It should not be crossing over that line. It's kind of hard to tell because I kind of messed that up here a little bit. But so again, if you measure the rise versus the run, so in this case, I have a very high rise, a small run. I'm going to have a steep slope. In other words, I'm going to have a large rate. So if they're dealing with a driving vehicle here, at this point in time, right here, I'm going pretty fast. If I were to do the same thing, say, right here, at this point in time, and I draw a line tangent to that point, one thing to notice here is that, let me finish drawing this here, is that my rise is small, but my run is great. So the slope of this line is actually going to be relatively low. So again, with the instantaneous, you're only measuring a single point. Now for average, you're just looking at the measurement taken at 2 points in time. Usually it's at the beginning, at the end. It could be really anywhere, but most often you're kind of looking at towards the beginning and towards the end. So you have 2 points, and you'll find the slope of the line that intersects those 2 points on the graph. So in other words, if I want to know what is my average speed from this point to this point here, let's say this is a unit of time down here. Make this a unit of time. So at this time versus this time, all I have to do is draw a line that goes from this point to this point right here, and measure my rise versus my run. And that would be my average. Now, one thing to keep in mind here is that if you look at my average versus my instantaneous, they're exactly the same thing if the lines are straight linear. Now, what's going to be different is if you have a curved line like we have down here. If I want to find the average here, what's going to happen here is, so like very early on and towards the end, I want to know what is my average here. Again, you just draw a line from those 2 points, and you measure the rise versus the run. Again, if I'm measuring time down here, it does not take into account all the different variations of my speed along this path here. It's only looking at the beginning and end. So if you look over here with instantaneous, here I had a high rate and a very low rate. Here, you can't measure that because you're just looking at beginning and end. Again, it's kind of like driving in a car to a certain destination. This would be like looking at your speedometer, whereas this is like saying you're this many miles away and it took you this period of time. That is your average. Hopefully that makes sense here. All right. So the way that we end up measuring the rate, so the general way of measuring the rate of reaction is in terms and change in concentration per unit of time. So like speed is distance versus time. A lot of times we're going to be measuring concentration per time. So the rate is a change in concentration over a change in time. Again, the triangle here means a change of. And typically, whenever you see the triangle, you're taking the final minus the initial. And the same thing, because it's a change in time, you're taking the final time minus the initial time. So to kind of simplify it, a lot of times they write out this way here. But the triangles, you always see final minus initial, final minus initial. So, and again, square brackets means concentration of in whatever substance A is. So most often the unit for concentration is molarity. The unit for time is in unit seconds, so therefore the unit is a molarity per second. And just a reminder here too, the molarity is the mole per liter. So one way of substitute, if you look at the units of this, it's a mole per liter per second, or molarity per second. So the reaction rate is a change in the concentration of a reactant or product with time. So in other words, molarity per second. So if I'm going from substance A to substance B, so A is my reactant, B is my product. So if you're measuring the rate of A, again, you look at the change in the concentration of A versus time. But one of the key things here is that this has a negative value to it. B, on the other hand, well, you could also be measuring the production of B as the change of B over the change in time. But this has a positive value to it. Now, the reason why this has a negative value is because you are losing material. And if you were to graph this out, like for A, I'll do this over here. Typically, A is your reactant. You're going to have a high amount. As time goes on, this is going to be sloping down. And the general shape of that line is a negative slope. That's the reason why you have a negative value, because you're losing material. Basically, you're subtracting material. B, on the other hand, if I were to graph this out, B is a product. Well, when the reaction first takes place, there is no B. So you have very little amount of it. And as time goes on, you have more and more, so it tends to curve upward. And you end up having a positive slope. That's the reason why this has a positive value to it. So sometimes we ignore the positive and negative if we're just kind of looking at absolute terms here. But technically, if you're dealing with the reactants will always be negative. Products will always be positive because you're losing material and you're gaining material. So for the reaction A to converting it to B, there are two ways of measuring the rate. First is the speed at which the reactant disappears. In other words, how quickly does A is being used up, or also be looking at the speed at which the products appear. In other words, the products being B, at what rate does B begin to increase? Now, one way to think about this is kind of like people walking from one room into another room. So if you have a room on the left and another room on the right, let me draw this out here. So if I have a room here, and I put a divider in between here, and I have, so this is basically my reactants, and these are my products over here. So I have all these individuals over here. Okay, but then these are individuals or particles, it doesn't matter what it is. And they are switching from going from A to B. So they're all moving in this direction. So as you lose stuff here as you reactant, you're also gaining it as a product over here. So as it begin to leave the room from your left to your right, it doesn't matter here. So you could be looking at the rate at which these things are disappearing, or you could be looking at the rate at which these are appearing. Hopefully that makes sense. So the average rate of a reaction over each interval is the change in concentration divided by the change in time. So if I'm looking at this would be butyl chloride I could be looking at the average rate of that. So each one of these would be, if I'm looking just between this and this, I could find out what is the average rate between those two time periods for that 50 seconds. And I could find out what is the rate at which the concentration is changing. Or I can go by longer units of time. And in doing so here, you'll get a kind of a wider, broad range of average. Now, one thing to note here, the average rate decreases as the reaction proceeds. So if you notice here, when the reaction first takes place, right here at the very beginning, you have a large amount of molarity changing over. And as time goes on, the value begins to drop. So this is because as the reaction goes forward, there are fewer collisions between the reactant molecules. Now, one way to kind of think about this is think about if you are in a crowded room and you have, and it's just full of people, and all of a sudden there's a game going on, and someone tells you you have to link up with one other partner, so it can only be groups of two, and you have to do it as quickly as possible. Well, you would have a huge mad rush of people linking together, and right at the very beginning, you're going to have a large number of couples being joined together. Now, as time goes on, there's going to be fewer and fewer couples being available here, but you're going to have some people who are going to be shut out. And you may have, say, within a large room. So let's say the X's represent the couples that join together. You know, this is so much easier on a marker board than on a computer. I really wish we were back in class. So you have all these couples here, but then you would have, you know, initially there was no couples here initially, but then as more and more kind of get shut out, you're going to have these individuals, and they're going to be kind of further and further apart. And what's going to have to happen here is, like, for example, in Earth, like for these two, they're going to be bouncing into all these other couples that have already been in the room, and it's going to be getting harder and harder for these two to come together, you know, for these last four to be able to join up, because they're now being crowded out by all these other couples. So that's one reason why, as time goes on, the reaction begins to slow down. It'll keep on going until everyone has found a partner here, but it just gets harder and harder, especially if you have a jam-packed full room full of people all trying to join up into couples. So if you look at this reaction, a plot of the methyl chloride versus time for this reaction yields a curve like this. In other words, if you look at this, so initially you're going to have a rapid change, and as time goes on, this slope begins to lessen out, or begins to kind of curve outward. And if you notice, the slope of this line is very steep, and over here it becomes more gradual. So the slope of the line tangent to the curve at any point is the instantaneous rate. So, you know, if I, right here at the very beginning of it, if I draw a line tangent to that arc, I'm going to have a very high rise, a small run. So I'm going to have a high rate of change taking place. Here, the rise is not nearly as great, and the run is a bit longer. And so I'm going to have a lower slope. So again, this is kind of similar to finding the instantaneous velocity of an object on a graph. You find the slope of a tangent line on the graph. So let me just kind of quickly go back to this here, is that, you know, on a curved line, what you're doing here is you find a single point and you draw a line tangent to that arc. And you're just looking at the rise versus run. All right. So all reactions slow down over time, and therefore the best indicator of a rate of reaction is the instantaneous rate near the beginning of the reaction. So if you want to kind of get a good sense of how quickly the reaction is taking place, a lot of times as the the reaction when it first takes place is a good indicator. The reaction has been going for a period of time. Almost all reactions will begin to level out to the point where they basically become almost level lines. And at that point, it's kind of hard to tell if the reaction has been taking place over long periods of time. So, for example, if I have something like this, you may have a reaction that kind of goes like this, and all of a sudden it just becomes flat. So if I measure it here, and later on I measure it here, but I didn't measure at the beginning of it, it's kind of hard to tell. Basically the slope is nearly flat. And it's kind of hard to tell how quickly was the reaction taking place without also measuring right here at the very beginning of it. So a good indicator of how the reaction is going is measure the reaction at the very beginning of it. So in this reaction, the ratio of methyl chloride, which is this right here, to methyl hydroxide, I'm sorry, it's not methyl, it's butyl. So this is butyl chloride, and butyl to butyl hydroxide is a 1-to-1 ratio. So this is a balanced reaction. You have 1 mole of butyl chloride is in ratio to 1 mole of butyl hydroxide. So again, just look at the coefficient numbers here. So the rate of disappearance of butyl chloride is the same as the rate of appearance of the butyl hydroxide. So in other words, for every one of these that are used up, one of these is also being produced here. So one thing you can say here is the loss of the rate of butyl chloride over time is the same as the increase of butyl hydroxide over a period of time. Again, if you notice your reactant has a negative value, your product has a positive value, these two are going to have the same rate because this is occurring at a 1-to-1 ratio. Later on, we'll get into what happens when they're not at a 1-to-1 ratio. So here is a little exercise. I'm going to kind of introduce this to you here a little bit, and then I want you to answer the question and select the best choice. And then after you make your selection here, we'll reveal the answer here. So let's try this first practice. The isomerization of methyl isotriol to acetotriol was studied in the gas phase at 250 degrees Celsius, and the following data were obtained below. Calculate the average rate of reaction in molarity per second from time 0 to time 15,000 seconds. Now, let me back up here just a little bit. The isomerization, if you remember back in Chem 1 here, an isomer is a chemical that has the same formula that has a different structure. And that's one where, if you remember, I gave you the formula and told you, I think there was like 5 or 6 different isomers of that compound. So they all have the same formula, but they just are arranged differently here. And if you notice, this one is CH3NC, whereas this one is CH3CN. They both have the same formula, but how they're put together are different, and those are what's called isomers. So basically, you're converting this into this. So even though they have the same formula, they have different types of structures, and they also have different types of characteristics. Now, but the question here is, we're looking at what is the rate of change, what is the average, and this is going to be one of the key things here, is that we're looking at the average rate. So from time 0 to 15,000 seconds. Okay, so what you want to look at is you're looking at what is the rate. Okay, that should be that little line. It's not a Z here, but you're looking at the concentration, CH3 and C. Yeah, this is not easy to do, over the change in time. Okay, and this is the change of concentration over the change in time. So if you remember, you're taking the final, minus the initial. Same thing for the taking the final time minus the initial time. Dot the I up here. So here is your final. Here is your initial. Okay. So I want you to calculate this. This is pretty straightforward. And if you remember, concentration is measured in molarity. So this is pretty straightforward one here. What is the average rate of change of this reaction here? If you're looking between 0 to 15,000 seconds. Okay, so work this one out. Select your choice, and then I will reveal the answer. Good luck. All right, now hopefully you did well. And let me show you the answer to this. So the setup for this is you're taking the change of this compound here over change in time. So you're taking the final, so 0.0074. I said this was the final, and this up here was the initial values. So I'm taking this concentration, 0.0074, minus my initial, 0.0165. So this is my final. This is my initial. And the final time was 15,000. And the initial time was 0. That's the reason why you see these 15,000, 0. So you subtract these two, you divide them, and you should get a value of 1.051 times 10 to the negative 6 molarity per second. That means every second the concentration was changing by this much of molarity. So in other words, if it didn't speed up, it didn't slow down, it maintained a constant rate, this would be the rate at which this substance would be changing. So hopefully you did well on that question. And we're going to go ahead and move on and try another one. All right, now the isomerization of methyl isotriol to acetyl was studied in the gas phase. So this is the same problem here. But this time you're going to be looking at graph the CH3NC versus the time and determine the instantaneous rate at 8,000 seconds. So previous one was the average. This time is now going to be the instantaneous. So so your instantaneous rate here. So at 8,000 seconds, which is right here, this is 8,000 seconds. I'll draw a little point right here. What you need to do is find out what is the change, the rate change at this point in time. So this is kind of like looking at your speedometer and see what's happening here. So if you need to, go back in the video here to see what you do with instantaneous. Do the best that you can on this one here. Probably many of you are probably looking on a screen here and trying to come up with the answer here, but this one might be best if you want to put these values in a spreadsheet and plot this out, or if you want to print this out, you can use a ruler here to find out the slope of it. I will tell you this though, do not make the mistake here of saying, well, it's rise over run here, where you can just take this rise versus this run. Okay, oops, didn't mean to happen here. So do not do that. Okay, that only works if this is a straight line. But because this is a curved line, you cannot do that. All right, so let me see if I can try to get rid of that here. Maybe I can't. Maybe not. Let me try some here. Okay, there we go. So once again, find out what is instantaneous at 8,000 seconds, this point right here. So go and work this one out and put in your choice. And then after you put in your choice, you will see the correct answer. Good luck. All right, so hopefully you did well on this one here. Now, for this particular case here, some of you um, may have gotten a little bit different answer, and it just kind of depends upon how much you end up drawing um, this line here. Now, the one thing I would recommend doing is making this line as long as possible, and um, typically the longer it is, you have a little bit more material to measure here. The slope of the line does not change. Okay, so, or if you draw this line right here, you measure the slope at this point, it's going to be exactly the same as over this whole triangle. It just makes it a little bit easier when the triangle is a little bit larger to read here. So all you have to do is, again, you're just taking your final minus your initial here. So if I drew this line like I have drawn here, this would be like my final, and this will be my initial values here. And if I were to take the time at this point right here, and this is my time at my initial one here, so that's where I got these two values down here, and then also my change in concentration here, actually, so my final here being 0, my initial up here I estimated about 0.007 molar, and by taking those values over here, I should end up with a value about like this. Now, oops, didn't mean to do that. Some of you may have gotten a little bit different answer, and that's okay. It just kind of depends upon if you're just slightly higher or lower, that might change your answer here a bit. Or just how well did you read those values here, that can also influence your rates here a bit as well. So hopefully you did well on that one. So let's try another one. All right, the decomposition of bromate follows the following reaction. And I have the reaction written down through here. A concentration versus time curve of the reaction was determined by the kinetics experiment below. What is the average rate over the first 12,000 seconds? I'm sorry, 1,200 seconds, not 12,000. So over the first, so a couple of key things here is you're measuring the average rate, and this is the first 1,200 seconds. In other words, first 1,200 seconds will be starting from here, and 1,200 seconds will be right here. So all you're doing is finding the average between those two. Okay, so you already did a problem similar to this one here. Try this one again and see how do you do. All right, now hopefully you did well on this one. So let's go ahead and take a look at the answer. So the final concentration at 1,200 seconds. So I'm looking at this point, 0.45. The initial was at 1 molar, and the final time was 1,200, and the initial time, the starting time, was 0 seconds. And so you should end up with a value about like this. Now, whether you come up with a positive or negative, technically it will be negative, but if you left it positive, that's okay too. So all we're doing is just what is the rate of change here. Technically, you're losing material here, but whether you left it positive or negative, in this situation, it doesn't matter. All right, so let's move on. Now, for this one, basically the same question, but the concentration versus time of the reaction was determined by the kinetics experiment. Below was the instantaneous rate at 800 seconds. So again, you're looking at the instantaneous rate of it. And I went ahead, because it's kind of hard to tell what exactly it is 800 seconds, so I went ahead and marked this one here. So at this point in time, what is the rate of change at 800 seconds? Not the average of it here, but the instantaneous rate. And again, if you need to, you can go back towards the beginning here to find the differences between average and instantaneous. So go ahead and figure this one out, put in your answer, and good luck. All right, so hopefully you did well in that one. And let's go ahead and take a look at the answer. So you have to draw a line that runs tangent to that line here at this point. And I get the initial concentration. I just drew it from edge of the graph to the edge of the graph here, just to make things a little bit easier here. Concentration is roughly 0.9 all the way down to 0, and the time, the final time, I'm estimating about 2,250 all the way up to 0 seconds. So I'm getting a change here about 4 times 10 to the negative 4th molarity per second. So at 800 seconds, this is how quickly their concentration is changing by. All right, let's move on. All right, so this is where I'm going to leave off for now. Go ahead and work those problems out, and later on, hopefully later on this week, we'll start getting into reaction rates and stoichiometry. And this one can be a little bit confusing. I'm going to kind of hopefully approach this a couple different ways here, and hopefully you guys will understand this here. So I hope that helps. I hope you found this interesting. Again, this will be a lot easier in a classroom, but I know you guys can do this here. So if you have any questions, feel free to email me, and good luck. Take care of yourselves, and I hope to see you guys soon. All right, take care. Bye-bye.